Hi, I'm Bushin Kim, and my Z ID is 5362155. So first, we can see the moon is traveling around Earth in a perfect circle, but this isn't always the case as it can come in oval-shaped parts or an ellipse, and this is the first Kepler's law. So the Earth moves by wiggling around its center and sways away from the moon, but doesn't seem to significantly distance away from its starting position by using the grid lines as reference. And since the Earth is a lot heavier than the moon, the center of mass of the Earth-Moon system would be inside the planet. And even after doing calculations, it shows that the radius is around 1600 kilometers longer than the center of mass. Now, if the Moon-Earth system still had its center of mass inside the radius width of the planet, there's a guaranteed chance that the center of mass between the Sun and a planet is also inside the bigger entity, which is the Sun. And for all three scenarios, the center of mass should be really close to the very center of the Sun. And I know we're supposed to just take a rough estimate, but just to make sure, I wanted to calculate the center of masses for each different scenario. And just like my estimate, no matter how much I change the masses of the Sun and our planet, the point always seems to stick very close to the Sun's center as shown in the bottom diagram. And therefore, the planet moon and some planet center mass are less than the radius of the bigger entity. Still, just because of how much bigger the Sun is than the Earth, the center of mass of the Sun is way closer to the center compared to the Earth-Moon system. And the distance between the center of the star and the planet were exactly 2 grid lines. And since that distance is measured as 1 astronomical unit, the red line is 0.5 AU. And we can see that the 4 scenarios follow the second Kepler's law. Planets move faster when they're closer to the Sun and vice versa. So as long as the Sun covers equal areas over equal times, the results seem to follow the third Kepler's law as well, since after I squared the orbital period for all 4 different scenarios and divided it by the distance in AU, the constants were approximately 111,000 except for the trial with 2 astronomical units, 140,000. And I would expect Mercury, that's closer to the Sun, to have the fastest velocity, since the derived equation for orbital velocity from Newton's law and centripetal force shows v is inversely proportional to the square root of the distance, making Neptune, which is the furthest away from the Sun, to be the slowest. Overall, I learned how to apply Kepler's law, especially the third one, to determine fascinating facts about the Sun and the planets around us, such as their orbital velocity, period, and varying distances.